All right, so guys, today section 8.4, the determinant of a square matrix. So I'm curious, how many of us, when we see the word determinant, how many of us remember what that's all about? One, maybe two hands. So far, two. Getting some of these, maybe. So maybe we'll push that to a few halves in there, so maybe 3.5 after counting it up. All right, so and again, time will tell. We'll see here in the next few minutes if this turns to an accurate statement or not. But usually, what has happened in years past has been that once we start doing the problems, then students are kind of like, oh, I remember what that is. I didn't remember it's called a determinant, but I remember doing that. So again, I know that I say this fairly often in here, but I just don't feel comfortable saying certain things are easy or difficult. But I will say that by the end of this chapter, by the time we're ready to take that test on Friday, determinants are not going to be at the top of your list of things that you're worried about. Again, the math is relatively simple. We are quite literally going to be multiplying and adding numbers together. That's it. And again, if we can do that, and then there's a subtraction problem at the end. So again, kind of like so many of these other things that we've been doing, again, there are just a lot of computations that take place, but each individually is really simple. So again, that's kind of where we're going. So the determinant of a square matrix. Again, we talk about the square matrix again because kind of like the inverse, we can't find the determinant or identify a determinant of a non-square matrix. So everything we're going to be talking about today, again, is going to be the square matrix. So the goals that we have in mind, goal number 1, students be able to find determinants of 2x2 matrices. And then goal number 2, now the students be able to find the determinants of all square matrices 3x3 and larger. So why not just lump this together in one goal and say we want to be able to find the determinants of square matrices? Again, we could have, but again, I'm just trying to make it clear that we actually have a different way we're going to go about the 2x2 as compared to the 3x3 and larger. All right? So, a determinant. All right. Hopefully this is the easiest question that you're asked all day. Is a matrix a number? A matrix is not a number. It's a way of organizing our elements. It's a way of organizing numbers. It's a way of putting it together. And again, it's represented with numbers, but a matrix, if I were to say, all right, yeah, there's matrix A over there, it's not like that, oh, okay, yeah, that's 7. Like, that doesn't make any sense. It's not a number. A matrix, it's a matrix. I realize that just sounds dumber and dumber as I keep going, but I can't think of another way to say it. A matrix is not a number. Now, we can identify, if we have a square matrix, we could calculate what we call the determinant, which now all of a sudden is going to associate a value, a specific value to each square matrix. Okay? So this determinant, and I know that we're playing off the word here quite a bit, but it's actually where the definite or where the phrase comes from. The determinant is going to help us to determine a lot of things moving forward. Okay? So really, the reason for section 8.4 is that, again, today, 8.4, and why I would say it's, I don't know, a more manageable day, is that it's all about, hey, let's just figure out how to find these things out. Let's figure out how to calculate these determinants. Because then when we move into tomorrow, it's all application. Okay? It's now tomorrow in 8.5 is, well, what can we do with these determinants? And there's a lot that we can do with them. There's a lot of things that you probably would never have associated. Like, we're going to teach you how to find the area of a triangle by using determinants. Well, what does a matrix have to do with a triangle? Well, I don't know. We'll show you tomorrow, right? Any questions? Nope. All right. I don't know if is one of these on your desk. Do you have one of these? Yep. Okay, good. All right. So we're also going to talk about how to, given a couple of points, how to write the equation of a line. What does that have to do with matrices? Again, we'll have to wait and see, tomorrow. But again, these determinants, they're going to have quite a bit of, like I said, application, and that's really in pre-calc what we're going with. You hopefully will recognize that you learned how to calculate determinants last year in Algebra 2. Okay, again, we may be a little shaky on the terminology that we call them determinants. Again, maybe you'll remember it when I say we're going to be multiplying diagonally going down, multiplying diagonally going up. So that's starting to sound a little bit more familiar. Okay, again, just when I said multiplying diagonally, I think I saw like 5 or 6 heads start to nod. A few people still shook their heads no, but that's fine. It's okay. All right, so here we go though. We say that here's our little definition. We said that every square matrix can be associated with a real number that's called its determinant. So we've been doing this with the 2x2 matrices since the day we introduced that formula. Okay, so that formula to find the inverse of a 2x2 matrix was always 1 over AD minus BC. Well, I think I slipped up way more than once, and I said it's 1 over the determinant, okay? Because AD minus BC, that was diagonally going down, diagonally going up, finding their difference. That is the determinant, okay? So for this 2x2 matrix, again, instead of using A, B, C, D, looks like here we're using A1, B1, A2, B2. So if that's the case, the determinant of A, which by the way, this is our notation. Kind of looks like the absolute value of A. The way that we would calculate that is multiplying diagonally going down A1 times B2 minus diagonally going up A2 minus B1. All right, now I do want to comment on this a little bit further. Again, I'm trying to be proactive here. Again, I have the luxury of foresight here. Again, I have the luxury of having done this. This is the 8th time I'm teaching pre-calculus. So I've seen some of the mistakes that students have made in previous years. And I've noticed that if I don't come out and say that this looks like the absolute value, but here's why it's not absolute value, again, some people are going to get the wrong idea. So even though this looks like the absolute value of matrix A, again, this is our notation for the determinant, okay? Please don't think of this as absolute value. Okay? The reason is that even if it's subconsciously, we all hear absolute value, we think everything has to be positive. So I'm just telling you here and now that it's going to be very possible that we will have determinants that are negative. There's nothing wrong with that. We're going to have negative determinants all day long. Okay? I would say about half the time the determinant's going to be negative. We're just as likely for it to be positive as it is to be negative. Okay? So please don't think that it's some kind of a special case or that we made some sort of a mistake or anything like that if we end up with a negative determinant. Guys, do we have any questions on that so far? All right, so like I said, the square matrix, pretty simple, pretty straightforward. We're going to figure out the product of the downs minus the product of the ups. So multiplying going down, again, talk about overdoing this problem. We're going to go 2 times 5, multiplying diagonally going up. We're going to go 3 times negative 1. So with your help, multiplying diagonally going down, 2 times 5 is 10, minus multiplying diagonally going up, 3 times negative 1 is negative 3. So 10 minus the negative 3 looks a whole lot like 10 plus 3, which is 13. So the determinant of that matrix A, again, so the way that we would write this out, the determinant of matrix A is equal then to 13. All right, so same thing over here with B. Again, probably don't need to play this one out as much. But if I were to multiply diagonally going down, 1 times 5 is 5, minus negative 4 times 0 is 0, and 5 minus 0 tells us determinant of B is. All right, guys, how do we feel so far? Hi. Thank you. So far, so good? All right, so do we all feel that finding the determinant of a 2x2 matrix, piece of cake so far, no issues whatsoever? All right, now, you knew what was coming. It can get a little bit more complicated. So, again, not the structure of the problem. Again, I really want to stress this, even before we do this next problem, that it's no different. Again, the way that we're going to go about this. But as we take a look at the given information in number 1 and number 2, and then what I should have labeled as number 3 down here, this next one, what do we notice about the matrix itself? If you look closely, say it again. Yeah, if we look more closely even at the brackets, what do you notice about 1 and 2 up top and then this third one down here? Everybody see it?
Does it have brackets?
Yeah, so again, this is saying the determinant of this 2x2 matrix is 0. So we're not trying to find the determinant here. We actually know the determinant is 0. Whereas up here in number 1 and number 2, with these being brackets, again, 2, negative 1, 3, 5, that was just a matrix. And it was our job then to find the determinant. So again, we didn't write it out this way. But what we were doing was finding the determinant like that. Okay? Down here, we already have those brackets. So we're being told that this determinant is equal to 0. So our task is actually to solve for x. What value of x is going to make the determinant of this 2 by 2 matrix equal 0? So again, the good news is we're not going to do this any differently. We're going to figure out the products of the downs minus the product of the ups. It's just that in this case, when we multiply diagonally going down, don't we have x plus 4 times x minus 5? The easy part is when we multiply diagonally going up, we have 7 times negative 2. Okay? Well, we're told that when we do that, the product of the downs minus the product of the ups, that's going to equate to 0. Again, that difference is going to be 0. So our task at hand is to actually multiply out x plus 4 times x minus 5. So, the double distribution, FOIL method, if you will. Again, multiplying the first terms, we have x squared. Outside is going to be negative 5x, inside 4x, so together negative x. And our last term then negative 20. I think we can hit this all in one step here. What's 7 times negative 2, please, sir? Negative 14. So plus the negative 14 is going to be looking more like that. So minus negative 14, I should say, is going to be plus 14. I think I misspoke on that. But do we all agree that this is where we're at? So do we have any like terms that we could combine? The negative 20 and the 14. So we can now say that we have x squared minus x minus 6 equals 0, and then now we have a factoring problem on our hands. So true question here becomes what multiplies to negative 6 and adds to negative 1? Negative 3 and positive 2. And if I set x minus 3 equal to 0, what do we know about x then? It's 3. If I set x plus 2 equal to 0, what do we know about x then? Okay, so my answers would be negative 2, positive 3. Those are the values for x. Now, let's just be as realistic as possible. Did we do anything differently on this last example? Did we do anything differently in terms of finding the determinant? No. But was this problem more challenging than the other two? Absolutely. There was just more to do, right? Again, we had more unknowns, we had variables, but it's again, if I could stress anything with a problem like this, it's that we didn't all of a sudden now magically find or calculate the determinant any differently. Okay? We just need to be prepared for a problem like that. All right, guys, next up, the determinant of a square matrix 2 by 2 or greater. We say that if A is a square matrix order 2 by 2 or greater, the determinant of A is found by using a little trick. So for matrix A, if we're looking at this, basically what I'm getting at is that if we have a 2 by 2 matrix, no big deal. When I multiply diagonally going down, when I multiply diagonally going up, we're hitting all 4 elements, aren't we? So we're happy with that. But when I move on to a 3 by 3 matrix, look at what happens when I multiply diagonally going down. We have A times E times I. Then diagonally going up, we have G times E times C. Did we hit all 9 of the elements? No. In fact, we missed 4 of them. Okay? We didn't hit B, D, F, or H. Then also we hit E twice. These are problems. Okay? So instead, we have a little trick. And again, something tells me you're going to remember this little trick from previous years. What we need to do is we need to take this first column, and we're going to rewrite it in what I usually call the 4th column location. We're going to take this 2nd column and write that in the 5th column location. Okay? Once we've done that, now when I multiply diagonally going down, we have 3 opportunities. And if you just go through your alphabet in your head right here, we have A, B, C, D, E, F, G, H, I. Yeah, we hit all of them. Okay? So we hit all 9 numbers, or all 9 values, I should say. Now what about diagonally going up? A, B, C, D, E, F, G, H, I. Yeah, we're hitting all of them. Now before we look at this and say, wait a second, we missed some. We missed this guy here. We missed this one over here. Did we already hit D both down and up? Did we hit E both down and up? Yeah, so we are good as long as we do this way. So again, that trick, once again, I'm putting air quotes around trick, is that we just take the first 2 columns and we rewrite them in the 4th and 5th column locations. As soon as we do that, then it's going to be no issue, no problem for us to multiply diagonally going down and diagonally going